let's go back and look what we did. We chose what we thought was an inside function, and if you make a mistake, what are you going to do? Throw your hands up and say, I told you I couldn't do this stuff? Or you can go back and try something different. Okay, so you can go back and try something, because every now and then we do make a mistake on that. So we're going to try t to the fourth plus 5. It seems to be an inside function of the integrand, and so it seems to be appropriate. And we take the derivative, and then we multiply both sides by the differential t. We look up and we realize that we've got every bit of that differential u up here, but we don't have the 4. And so if we divide both sides by 4, now I've got this whole piece right here that matches this piece up here. So if I make a substitution, in place of t to the fourth plus 5, I put u, and in place of t cubed dt, I put in 1/4 du. I'm on my way. I take the integral of that. But when I get done with that, I have to remember my problem is in terms of t, not in terms of u. So I go back and do a second substitution and come up with my function f of t. Easy stuff. We can always make it a little more difficult. Not difficult, that's the wrong word. Challenging. A little more challenging by just throwing in a different problem. So let's take a look at this one. Okay, let me remind you that what we are doing is the integral of a composite function. Nothing has been said about taking the integral of a sum and applying the same rules to it. But did you remember that theorem that says that if you have the integral of a sum, it's the same thing as the sum of the integrals? So let's break this apart. And while I'm doing that, I'm going to make this 3x to the negative 2. Now, one of those integrals is pretty easy. The first one, not bad. I bet you have it in your head right now. You can almost do these now in your head, right? Add 1 to the exponent, divide by the new exponent. So the first one is going to be pretty easy. That's just going to be x cubed divided by 3 plus c. It's the second one that we have to work on, because it's a composite function. Okay. So we got the first one done. We're going to kind of just leave it there. We're not going to do anything else with it just yet. But let's think about this. Off to the side, we're going to say let u equal. And what will you let it equal of this?
3x.
Yeah, the inside function, 3x. Not 3x squared, just 3x. Okay? What's the next thing? Take the derivative of it, okay? Now, if you do this enough, you kind of can think ahead, where am I going? Why am I doing this? What do I need to have in place? We're wanting to take this and write it in terms of u, or du, u and du. And I have a dx over here, so my next thing is to, so I'm going to say du equals 3 dx, but what? Yeah, I don't have a 3 dx over here. I just have dx. So if I divide both sides by 3, then I would have, in place of dx, I can put 1/3 du. And in place of, in place of 3x to the negative 2, I now have u to the negative 2 times 1/3 du. Again, that scalar of 1/3 can be written as, bring it out to the front, I'm just going to keep bringing this down. Remember, this piece is done. We don't have to work on this piece at all. And now this becomes a nice little, just a simple little integral to take. You'll stop me if I make a mistake, right? Good. So now, I didn't put up here that this was our first substitution. Down here now, we'll do our second substitution. Because, you know, and again, I think it would help if at this point you remind yourself what you've got. It's a little odd. I've got an x and a u, but at this point, if you want to, I'm just going to say I have the function, okay? I don't want to say f of x because I've got a u in there, but I've got, you know, this is the function. So if I come down here, and what I'm wanting is to have the function in terms of x, well, the first piece I've got x cubed divided by 3 plus c. The second one I don't have, but can I make it that way? 1 divided by 3 times what? 3x plus c. And so f of x now is x cubed divided by 3 minus 1 divided by 9x plus c. How will you check it? Take the derivative, okay? Or, yeah, I want you to know, I want you to realize if you take the derivative of this, you should get back to that integrand. Let's see, if this is 1/3 x cubed minus 1/9 x to the negative 1 plus c. If I take the derivative, 3 times 1/3 is 1, leaving me with x squared. Negative 1 times negative 1/9 is 1/9, leaving me with x to the negative 2. Is that right? Yeah, because I'm taking 3x quantity squared. That'd be 9x. Is that the same thing? And it is. Okay. And we don't have the, well, that wouldn't be plus c, though, would it? Because that becomes a 0. Okay. So we're let's go back and look at this problem. We've got, we first of all realize that because it's a sum or a difference, we're going to break it into multiple integrals. And one of those becomes very easy then to work with, so we just did that. The second one is a composite, so this is where we have to use our alternate, our other idea, our substitution idea. And we choose the inside function, take its derivative, multiply both sides by the differential. Why? Because we want to substitute something for this right there. Okay? And so we end up being able to substitute this quantity, 1/3 du, for that dx. That then becomes a pretty simple little integral here. And I can do the integration using the rules that I know. But then I have to remember, I have to put it back in terms of the original input variable. So I go back and do a second substitution, and I've got my answer. What happened to the c and the c? They're just any, you know, any constant times it, or plus any constant is still any constant. So Again, not something you go back and tell your Algebra 1 relatives about. Okay. Okay, thumbs up, thumbs down, thumbs not sure. Okay, everyone, it's really not that difficult. It doesn't have to be. But then again, we can give you some more challenging problems if we want to. We've got some time. Let's take a look at this one. When we say solve the differential equation, we have to know what that means. So what we're trying to get to is what? Yeah, find the function, okay, that has this as a derivative. Okay. I would start this way. Give myself the integration symbol. I'm going to actually do x minus 4 and then make this denominator and then this is dx. I want to ask you something. We say this is our derivative. This. If you take this that you're given and multiply both sides times dx, what do you get? dy. So this is really, let's see, we get dy. Actually, I can't stop there. This whole thing is dy if you multiply both sides by dx. Just thought I'd bring that out to you. Okay, just let you see that. That's absolutely true. It is dy. It is the differential y. Okay, now, can we separate this like the last one? Two different integrals? It's not a sum or difference, okay? So the answer to that would be no. We can't separate it. If it's a sum or difference, we can do that. So we're going to have to use our chain rule. So that means that I'm going to let u equal, and I'm going to let you tell me what that should be. Let u equal what? Do you see an inside function? Go for that. Yeah. Yep, absolutely right. Go for the inside function. What's the next step? Okay, the derivative of u with respect to x. Go ahead and take that. I'm also going to just rewrite the original integral to put the x minus 4 and the dx beside each other. In fact, I could even put those inside brackets. Separate it from the composite part of it. Okay, so I take the derivative. Are you getting 2x minus 8? What do you want, Chelsea, out of this? You don't want 2x minus 8. What do you want? So that it matches this. We can do that if we do, take a 2 out, factor out a 2. Always looking ahead. Why am I doing this? What is it that I need? What needs to be in place for me to make that first substitution? Because we're going to do a substitution here in just a little bit. And so now I've got this, so now I multiply both sides.